Hello, thanks for playing my video. On this video we'll be proving the spherical Pythagorean theorem. In order to do this, I'm going to presume that you know the following topics. Those topics are vectors, spherical coordinates, arc length, and some basic trigonometric functions. So let's get started. In ordinary flat space, if we have a right triangle, we know that Pythagorean theorem says that the square of its base added the square of its height will be equal to the square of the hypotenuse. And as a consequence of this, we can find the distance between two arbitrary points in the Cartesian plane just by having the coordinates of each point. Now, why am I mentioning this? Because in order to prove the spherical Pythagorean theorem, at least in this case, we'll be proving it as a special case of a formula that calculates the distance between two arbitrary points on a sphere. So please keep that in mind. Now, what does the spherical Pythagorean theorem says about right spherical triangles? Well, it says the following. If we have a right spherical triangle with hypotenuse C, base A, and height B, the theorem says that the cosine of its hypotenuse is equal to the cosine of its base multiplied by the cosine of its height. And this formula we'll be proving in this video. Now, remember that this formula will be proved as a special case of a formula that calculates the distance between two arbitrary points on a sphere. Just like in the ordinary flat case, where we know the distance just by having the coordinates of the Cartesian in the Cartesian plane. So, what do coordinates look like on the sphere? Well, in spherical coordinates, we can define the position of each point by the radius of a sphere, we're going to call it rho, by an east and west angle called theta, and a north and south angle called phi. Now, additional, we're going to need the rectangular components of each the coordinates, and I'll explain why later. So the rectangular version of rho theta phi looks something like this. Since we're measuring phi, consider that the initial position is in the equator, the transformation looks something like this. X will be equal to rho times the cosine of theta times the cosine of phi. Y will be equal to rho times the sine of theta times the cosine of phi. And Z will be equal to rho times sine of phi. Now, why do I need to convert from rho theta phi to x, y, z? Because in order to calculate the distance between 2 points on a sphere, I'm going to assign a position vector for each of those points. So how do we do that? Well, in order to find a position vector, we're going to need its rectangular components, and that's where the conversions come in very handy. So, if we have a point rho theta phi on a sphere, the position vector will be given by the rectangular conversion of these points, and it looks something like this. So, how do I go from vectors from calculating position? In order to do that, I'm going to need a vector for 2 points on a sphere, and if I know the angle between those vectors, I can assign that angle to the arc length formula. And how do we do that? Well, if we have two vectors, we know that the cosine of the angle between them is equal to the product of the vectors divided by the magnitude of each vector. So how does this formula apply if my position vectors are given by my spherical coordinates? Well, in order to do that, consider a unit sphere and 2 points on its surface. And by saying unit sphere, I'm saying that the radius is equal to 1. So rho will be equal to 1. So if I have 2 points, I'm going to label each vector with the index for my angles. A rho will not have an index because the radius is the same for all points on a sphere. And if I have the position vectors for each of those points, and I know how to calculate the angle between them, and since I'm considering a unit sphere, that means that rho is equal to 1, and since the vectors have an initial point in the center and an ending point on its surface, that's equal to the radius of the sphere. That means that the magnitude of each vector is also 1. So, keep in mind that point 1 and point 2, right here, is the position vector for points on a sphere. And if I have these vectors, and if I know how to calculate the angle between them, well, it's going to look something like this. The cosine of the angle is equal to the dot product of each vector, the dot product of the vectors divided by the magnitude of each vector. But since the magnitude of A and B is 1, it just reduces to the dot product between the vectors. So how do we calculate dot product? Well, we multiply the x component of P1 times the x component of P2, and then add the y component of 1 times the y component of P2, and then add the z component of 0.1 times the z component of 0.2. And if we add them together, and we apply the inverse cosine of both sides, we know that the angle is equal to the inverse cosine of cosine theta 1, cosine phi 1, cosine theta 2, cosine phi 2, plus sine of theta 1, cosine of phi 1, sine of theta 2, cosine of phi 2, plus sine of phi 1, sine of phi 2. And this is my formula for calculating the angle between two position vectors on a unit sphere. Now that I have my angle between them, I can find arc length. So, since I'm considering a unit sphere and rho is equal to 1, and the arc length is equal to the radius times the angle, and since rho is equal to 1, we have the special case that the length L is equal to the angle theta. So, that being said, let's take it out for a spin. Let's do an example. Let C be the distance between 0.1 and 0.2 on a unit sphere. And let's give each of those points a spherical coordinate. Let's label P1 as 1, the radius. Let's put the angles in their initial position. That means that theta is 0 and phi is 0. And now let's put another arbitrary point on the sphere with the same radius, but we're going to put theta as A and phi as B. And if we know how to calculate the distance between them, and I said that the distance between them is equal to the angle between them on the unit sphere, we have the C is equal to the inverse cosine of cosine theta 1, which is cosine of 0, cosine of phi 1, which is 0, cosine of A, cosine of B, plus sine of 0, cosine of 0, sine of A, cosine of B, plus sine of 0 and sine of B. But since cosine of 0 here is just 1, it just leaves cosine of A, cosine of B, and sine of 0 is equal to 0, so both of these terms cancel out. So we're left with this. C, the distance between them, is equal to the inverse cosine of the product of cosine of A and cosine of B. And for the grand finale, just apply cosine of each side, and we have the spherical Pythagorean theorem. Cosine of C is equal to cosine of A times cosine of B. Thank you so much for watching. I hope this was useful. If there are any questions about this, please feel free to comment. And I apologize for my bad English because it's not my first language. So thank you so much for watching.